Imagine stepping outside on a clear night, and instead of seeing just the familiar moon and stars, you look up to witness something absolutely breathtaking. Stretching across the entire sky like a cosmic bridge made of diamonds and ice, magnificent rings circle our planet, just like the famous rings of Saturn. This isn't just a fantasy from a science fiction movie. This is a legitimate scientific possibility that has captured the imagination of astronomers and planetary scientists around the world. The question isn't whether it would be beautiful, because it absolutely would be spectacular beyond imagination. The real question is whether our Earth could actually support such an incredible ring system, and the answer is both fascinating and complex. To understand whether Earth could have rings, we need to dive into some truly mind-blowing physics. Saturn's gorgeous rings don't just exist by accident. They exist within what scientists call the Roche limit, named after the French mathematician Édouard Roche, who figured out this cosmic rule back in 1848. The Roche limit is essentially nature's demolition zone, a special region around any planet where gravitational tidal forces become so incredibly powerful that they can literally tear apart moons, asteroids, comets, and other large objects. It's like having an invisible cosmic blender that shreds anything that gets too close, turning solid objects into countless billions of tiny particles that then spread out to form beautiful ring systems. For our Earth, this gravitational demolition zone is surprisingly close to home. Earth's Roche limit extends from approximately 2,000 kilometers all the way out to about 12,000 kilometers above our planet's surface. To put this in perspective, that's much closer than you might expect. Our geostationary communication satellites, the ones that bring us television signals and internet connections, orbit at a comfortable 35,800 kilometers above Earth. The International Space Station, where astronauts live and work, zips around our planet at just 400 kilometers up. So Earth's potential ring zone sits right in between these familiar orbital neighborhoods, creating a cosmic sweet spot where ring particles could theoretically survive and thrive. But here's where things get really interesting and a bit complicated. While Earth could technically support rings within this zone, our planet faces some serious challenges that Saturn simply doesn't have to deal with. Saturn sits out in the cold, distant reaches of our solar system, about 10 times farther from the Sun than Earth. Out there in that cosmic countryside, Saturn enjoys relative peace and quiet. The gravitational influences from other planets and moons are much weaker, allowing Saturn's rings to maintain their structure for millions and millions of years. Earth, on the other hand, lives in a much busier cosmic neighborhood. We're constantly being influenced by the powerful gravitational pull of our Sun, which is much closer and more influential than Saturn experiences. But even more importantly, Earth has something that makes ring formation incredibly challenging: our massive moon. The moon might look small and peaceful in our night sky, but gravitationally speaking, it's a cosmic bully that would constantly interfere with any ring system Earth might try to maintain. Our moon is unusually large compared to Earth. In fact, the Earth-Moon system is sometimes called a double planet because our moon is so big relative to Earth that they almost orbit around each other rather than the moon simply orbiting Earth. This creates incredibly complex gravitational interactions that would constantly pull and tug at ring particles, causing them to spiral inward toward Earth or get flung outward into space. It's like trying to build a house of cards during an earthquake. The constant shaking makes it nearly impossible to maintain any stable structure. The Sun adds another layer of complexity to this cosmic dance. Solar radiation pressure, the actual physical push of sunlight hitting tiny particles, would gradually alter the orbits of ring particles over time. The Sun's gravity would also create what scientists call secular resonances, special orbital relationships that can dramatically change particle orbits over long periods. These effects are much stronger for Earth than for Saturn because we're so much closer to our star. Despite these challenges, the physics clearly shows that Earth could indeed support a ring system, at least temporarily. The key word here is temporarily. While Saturn's rings have existed for hundreds of millions of years, and might continue for hundreds of millions more, Earth's rings would face a constant battle against destruction. They would need to be continuously replenished with new material to maintain their spectacular appearance. Scientists have run computer simulations showing exactly how Earth's rings would behave under these challenging conditions. The results are fascinating. Ring particles would follow complex, ever-changing orbits. Some would gradually spiral inward and eventually burn up in Earth's atmosphere like meteors. Others would be gravitationally scattered outward until they escape Earth's influence entirely. The rings would be dynamic, constantly evolving, and absolutely beautiful to behold. The density and composition of Earth's rings would also be different from Saturn's. Saturn's rings are made primarily of water ice, which reflects sunlight brilliantly and gives them their bright, clean appearance. Earth's rings would likely contain more rocky material mixed with ice, creating a different color palette and reflecting pattern. They might appear more golden or reddish compared to Saturn's pristine white rings. What makes this possibility even more intriguing is that Earth might have actually had rings in the distant past. Some scientists theorize that during the massive collision that created our moon about 4.5 billion years ago, enormous amounts of debris were blasted into orbit around Earth. This debris could have formed temporary rings that gradually coalesced to help form the moon we see today. If this theory is correct, then Earth has already experienced having a ring system, even if it was billions of years ago and lasted only a relatively short time. Modern technology has allowed scientists to model exactly what Earth's rings would look like and how they would behave. Using the same computer programs that track satellites and space debris, researchers can simulate the complex orbital mechanics of millions of ring particles. These simulations show that while challenging to maintain, Earth's rings would be absolutely spectacular and would dramatically change our planet's appearance from space. The mathematics behind planetary rings is both elegant and complex. The gravitational forces involved follow Newton's laws of motion and universal gravitation. But when you have millions of particles all influencing each other, the calculations become incredibly sophisticated. Each particle in the ring system would be subject to gravitational forces from Earth, the Moon, the Sun, and even from other ring particles nearby. The result is a constantly shifting, dancing display of cosmic mechanics that would be both beautiful and scientifically fascinating. One of the most remarkable aspects of potential Earth rings would be their incredible speed. Ring particles orbiting at the inner edge of our theoretical ring system, around 2,000 kilometers above Earth's surface, would be traveling at approximately 7 kilometers per second. That's over 25,000 kilometers per hour, fast enough to circle the entire Earth in just 90 minutes. At these incredible speeds, even tiny particles would pack enormous kinetic energy, making collisions between particles spectacular events that could create cascades of smaller fragments. The structure of Earth's rings would be far more complex than they might appear from a distance. Just like Saturn's rings, which appear smooth from Earth but are actually composed of thousands of individual ringlets and gaps, Earth's rings would have intricate structure. Gravitational resonances with the Moon would create gaps and divisions in the rings at specific distances from Earth. These gaps, similar to the famous Cassini division in Saturn's rings, would be regions where ring particles simply cannot maintain stable orbits due to the Moon's gravitational influence. The particles themselves would range in size from tiny dust grains, smaller than the width of a human hair, to boulders the size of houses. The smallest particles would be created by constant collisions between larger objects, grinding them down over time like a cosmic mill. The largest chunks would be remnants of whatever original object was destroyed to create the ring system in the first place, perhaps fragments of a shattered moon or the remains of a massive asteroid that wandered too close to Earth. Temperature would play a crucial role in the behavior of Earth's rings. Unlike Saturn's rings, which exist in the deep freeze of the outer solar system, where temperatures hover around -180 degrees Celsius, Earth's rings would experience much more variable temperatures. The side of ring particles facing the Sun could heat up to several hundred degrees, while the shadowed side would plunge to the extreme cold of space. This constant heating and cooling cycle would cause particles to expand and contract, potentially leading to fracturing and the creation of even more ring material. The gravitational environment around Earth is also much more dynamic than around Saturn. Our planet experiences significant tidal forces from both the Sun and Moon, creating what scientists call the Hill sphere, the region around Earth where our planet's gravity dominates over the Sun's influence. Earth's Hill sphere extends to about 1.5 million kilometers, much smaller than Saturn's Hill sphere, which extends over 65 million kilometers. This smaller sphere of influence means Earth's rings would be more susceptible to external gravitational perturbations. The formation of Earth's rings would require some truly catastrophic event. The most likely scenario would involve a large moon or asteroid approaching Earth and being torn apart by tidal forces as it crossed the Roche limit. This process, called tidal disruption, would be an absolutely spectacular event. As the object approached the critical distance, Earth's gravity would begin to overcome the object's own gravitational self-attraction. The side of the object closest to Earth would experience stronger gravitational pull than the far side, stretching the object like taffy until it finally broke apart into countless fragments. Alternatively, Earth's rings could form from the collision of two large objects within the Roche limit, perhaps two small moons, or a moon and a large asteroid. The impact would shatter both objects, creating a debris cloud that would gradually spread out into a ring system. This type of collision might be more likely than tidal disruption, since it doesn't require a large object to approach Earth from the outer solar system. The scientific community has actually studied this possibility quite seriously. Research papers have been published in prestigious journals examining the orbital mechanics, composition, and long-term evolution of hypothetical Earth ring systems. Computer models have been developed that can simulate the behavior of millions of ring particles over thousands of years, taking into account all the gravitational influences and physical processes that would shape the rings. So yes, Earth could absolutely have rings like Saturn. The physics works, the orbital mechanics check out, and computer simulations confirm that such a system could exist. The rings would be temporary on geological timescales, lasting perhaps thousands to millions of years, rather than hundreds of millions like Saturn's rings. But during their existence, they would transform our planet into one of the most beautiful objects in the solar system, rivaling even Saturn in their cosmic majesty and wonder. The scientific evidence is clear. Earth's rings are not just possible, they're inevitable given the right circumstances. Now that we know Earth could theoretically have rings, the next burning question becomes how long these magnificent cosmic structures could actually survive around our planet. This is where things get really fascinating and a bit heartbreaking at the same time. While Saturn's rings have been spinning majestically around the giant planet for potentially hundreds of millions of years, Earth's rings would face a cosmic countdown clock that would make their existence far more fleeting and precious. The lifespan of Earth's rings would depend on a complex interplay of forces that simply don't exist in Saturn's distant, peaceful corner of the solar system. Think of it like the difference between trying to maintain a delicate sandcastle on a calm beach versus trying to build one during a hurricane. Saturn sits in the cosmic equivalent of that calm beach, while Earth exists in the middle of a gravitational storm created by our proximity to the Sun and our unusually large moon. Let's start with the moon, our constant companion that would unfortunately be the primary destroyer of any ring system Earth might develop. The moon's gravitational influence on Earth is already responsible for our ocean tides and it would have an equally dramatic effect on ring particles. Unlike Saturn, which has many small moons that actually help maintain and sculpt its rings through gravitational shepherding, Earth's single massive moon would act more like a cosmic vacuum cleaner, constantly pulling ring particles out of stable orbits. The moon orbits Earth at an average distance of 384,000 kilometers, which might seem far away, but gravitationally speaking, it's close enough to wreak havoc on ring particles. The moon's gravity would create what scientists call resonant interactions with ring particles at specific distances from Earth. These resonances occur when a ring particle's orbital period becomes a simple fraction of the moon's orbital period, like 1/2, 1/3, or 2/3. When this happens, the repeated gravitational tugs from the moon at the same point in the particle's orbit would gradually change its trajectory, eventually ejecting it from the ring system entirely. Computer simulations show that these lunar resonances would create distinct gaps in Earth's rings, similar to the famous Cassini division in Saturn's rings, but much more pronounced and destructive. Over time, these gaps would grow wider and wider as more particles were removed, until eventually the entire ring system would be cleared out. The process would be like watching a cosmic eraser gradually removing beautiful celestial artwork. The Sun adds another layer of complexity to this destruction timeline. Solar radiation pressure, the actual physical force exerted by sunlight hitting tiny particles, would constantly push on ring particles, gradually altering their orbits. This effect, called the Poynting-Robertson effect, causes small particles to spiral slowly inward toward the planet they orbit. For Earth's rings, this would mean a constant rain of ring material falling into our atmosphere, creating spectacular meteor showers, but gradually depleting the ring system. The Sun's gravity also creates what are called secular resonances, long-term orbital changes, that can dramatically affect ring particles over thousands of years. These resonances are much stronger for Earth than for Saturn because we're so much closer to our star. The Sun's gravitational influence would constantly perturb ring particle orbits, making long-term stability nearly impossible without continuous replenishment of ring material. Earth's stronger magnetic field compared to Saturn would also play a role in ring destruction. Our planet's magnetosphere, the magnetic bubble that protects us from solar radiation, would interact with any electrically charged particles in the ring system. This interaction could cause ring particles to lose energy and spiral inward, or gain energy and escape outward. The net effect would be another mechanism constantly working to disperse Earth's rings. Atmospheric drag presents yet another challenge that Saturn's rings simply don't face. Even at the altitude where Earth's rings would exist, roughly 2,000 to 12,000 kilometers above the surface, there are still traces of our planet's atmosphere. These incredibly thin wisps of gas would create drag on ring particles, especially the smaller ones, causing them to gradually lose orbital energy and spiral inward toward Earth. This process would be slow but relentless, like air resistance gradually slowing down a spinning top. The collision environment around Earth is also much more hazardous than around Saturn. Our inner solar system location means we're constantly bombarded by meteoroids and space debris. These high-speed impacts with ring particles would gradually grind down the ring material, turning larger chunks into smaller fragments and eventually into dust that would be more easily dispersed by radiation pressure and atmospheric drag. So how long could Earth's rings actually last under these challenging conditions? The answer depends greatly on the initial size and composition of the ring system, but scientific models suggest timescales that are geologically brief. The finest particles, those smaller than a few centimeters, would be removed within thousands to tens of thousands of years due to radiation pressure and atmospheric drag. Larger particles might survive for hundreds of thousands to a few million years before being removed by resonant interactions with the Moon. This means that if Earth somehow acquired a ring system today, future civilizations living just 50,000 years from now might look up at a night sky where the rings had already faded to a faint shadow of their former glory. By 1 million years in the future, the rings would likely be completely gone, existing only in the geological record and perhaps in the form of unusual meteor shower activity. However, there's an important caveat to this timeline. If Earth's rings were continuously replenished with new material, they could potentially last much longer. This replenishment could come from several sources. Ongoing collisions between asteroids or comets within the ring zone could create new debris to replace what's being lost. The gravitational capture of passing space objects could add fresh material to the system. Most dramatically, the periodic disruption of small moons or large asteroids that wander too close to Earth could inject massive amounts of new ring material. The key insight here is that ring longevity is all about balance. If the rate of material loss equals the rate of material replenishment, rings can persist indefinitely. Saturn's rings have achieved this balance through a complex ecosystem of moons, gravitational resonances, and ongoing collisions that continuously recycle ring material. Earth's rings would need to find their own balance, but our planet's location and gravitational environment make this much more challenging. Interestingly, some scientists have proposed that Earth might have had multiple episodes of ring formation throughout its history. Perhaps every few 100 million years, some catastrophic event creates a new ring system that persists for a few million years before being dispersed, only to be replaced by a new ring system from another catastrophic event. This cyclical ring formation could explain some puzzling features in Earth's geological record, such as unusual concentrations of certain types of meteorites or unexplained climate variations. The destruction timeline would also vary depending on the distance from Earth. Ring particles closer to our planet would face stronger atmospheric drag and more frequent encounters with Earth's magnetic field, leading to faster orbital decay. Particles farther out would be more susceptible to lunar resonances and solar perturbations. There might be a sweet spot somewhere in the middle where particles could survive the longest, creating a gradual evolution of ring structure over time as the inner and outer edges erode away. Temperature cycling would accelerate the destruction process. As ring particles rotate in their orbits, they would experience extreme temperature swings from several hundred degrees on the sun-facing side to -200 degrees on the shadowed side. This constant expansion and contraction would cause thermal stress fracturing, gradually breaking larger particles into smaller ones that are more easily removed by radiation pressure and atmospheric drag. The composition of Earth's rings would also affect their longevity. Ice-rich particles would be more susceptible to sublimation, the direct transition from solid to gas, especially when heated by sunlight. Rocky particles would be more durable, but also denser, making them more susceptible to atmospheric drag. A mixed composition ring system would evolve over time as different materials are preferentially removed, potentially leading to compositional segregation within the rings. Despite these challenges, the temporary nature of Earth's rings would make them all the more precious and spectacular. Unlike Saturn's ancient, stable rings that have looked essentially the same for millions of years, Earth's rings would be dynamic, constantly changing, and absolutely unique. Every night would potentially bring visible changes as the ring system evolved and transformed. Astronomers would have front-row seats to one of the most spectacular ongoing shows in the cosmos. The scientific value of observing ring formation, evolution, and destruction in real time would be immeasurable. We would learn more about planetary ring dynamics in a human lifetime than we've learned about Saturn's rings in centuries of observation. The rings would serve as a natural laboratory for studying orbital mechanics, particle physics, and gravitational interactions on a scale impossible to replicate in any Earthbound experiment. So while Earth's rings would indeed be temporary, lasting perhaps thousands to millions of years, rather than the hundreds of millions that Saturn's rings have endured, their brief cosmic existence would be no less magnificent. In fact, their transient nature would make them even more special. like a rare celestial fireworks display that transforms our entire world into one of the most beautiful planets in the solar system, if only for a geological moment. Imagine waking up tomorrow morning and stepping outside to discover that overnight, Earth had somehow acquired magnificent rings, like Saturn. What would you actually see when you looked up at the sky? The answer is absolutely mind-blowing and depends entirely on where you happen to be standing on our planet. The view would be so dramatically different from different locations that it would literally reshape how humans think about geography, navigation, and our place in the cosmos. The key to understanding what Earth's rings would look like lies in a simple but crucial fact about how rings work. Unlike the moon or planets that we can see from anywhere on Earth's surface, rings lie in the plane of a planet's equator. This means that Earth's rings would stretch around our planet's middle, creating a cosmic belt that would appear completely different depending on your latitude, the time of day, the season, and even the time of night. Let's start with the most dramatic viewpoint, standing directly on Earth's equator. If you were in Ecuador, Kenya, Indonesia, or any other equatorial location, Earth's rings would appear as an incredibly thin, brilliant line stretching directly overhead from horizon to horizon. Picture the finest silver thread you can imagine, but glowing with the brightness of a full moon, dividing the entire sky into two perfect halves. This line would be so narrow that it might appear to be just a few degrees wide, but it would be impossibly straight and bright, like someone had drawn across the heavens with a cosmic ruler and the most brilliant marker imaginable. But here's where it gets really interesting. As you move away from the equator toward the north or south, the rings would gradually appear wider and more spectacular. If you lived in cities like Miami, Cairo, or Mumbai, which are roughly 25 degrees north of the equator, the rings would no longer appear as a thin line overhead. Instead, they would stretch across the sky as a magnificent arc, perhaps 20 to 30 degrees wide, spanning from one horizon to the other, but tilted at an angle that would make them appear as the most spectacular celestial bridge you could possibly imagine. Move further north to cities like New York, Rome, or Beijing, and the rings become even more dramatic. At these latitudes, around 40 degrees north, the rings would appear as enormous arcs sweeping across the southern sky. They would be visible as broad bands of light, potentially 50 to 60 degrees wide, creating an absolutely breathtaking canopy that would dwarf anything we currently see in our night sky. The rings would appear to rise from the southeastern horizon, arch high across the southern sky, and set in the southwestern horizon. The most spectacular views of all would be from mid-latitude locations like London, Paris, or Seattle. Here, at around 50 degrees north latitude, Earth's rings would appear as massive, glowing arcs that would dominate the entire southern portion of the sky. These wouldn't be thin lines or narrow bands, but enormous structures that would span nearly 90 degrees of sky, appearing almost like a second, much brighter and more detailed version of the Milky Way, but hundreds of times more brilliant and intricate. But what about people living near the poles? Here's where things get both interesting and a bit disappointing. If you lived in northern Alaska, northern Canada, Greenland, or Antarctica, Earth's rings would be extremely difficult or impossible to see. The curvature of our planet and the fact that rings lie in the equatorial plane means that from extreme polar latitudes, the rings would appear very close to the horizon, often blocked by mountains, buildings, or even just atmospheric haze and distortion near the horizon line. The brightness of Earth's rings would be absolutely spectacular, far exceeding anything we currently see in our night sky, except for the sun and moon. When optimally positioned and fully illuminated by sunlight, Earth's rings would easily outshine Venus, Jupiter, and even the International Space Station. In fact, they would likely be bright enough to cast shadows on the ground, just like the full moon does today, but potentially even more dramatically. The color of Earth's rings would depend on their composition, but they would likely appear somewhat different from Saturn's pristine white rings. If Earth's rings contained significant amounts of rocky material mixed with ice, they might appear more golden, amber, or even slightly reddish, especially when viewed through Earth's atmosphere during sunrise or sunset. The atmospheric filtering that makes our sun appear red when it's low on the horizon would have a similar effect on ring light, potentially creating breathtaking color variations throughout the day and night. The rings would be most visible during dawn and dusk, when the sun is below the horizon but still illuminating the ring particles high above Earth's shadow. This would create spectacular displays where the rings would glow brilliantly against the dark sky, while the ground remained in twilight or darkness. Imagine stepping outside just after sunset and seeing massive, glowing arcs of light stretching across the heavens, bright enough to read by, creating one of the most romantic and awe-inspiring sights imaginable. During the day, Earth's rings would still be visible, though much fainter against the bright blue sky. They would appear as pale, ghostly arcs, similar to how the moon is sometimes visible during daylight hours. The rings would be most visible during the day when the sun is at a low angle, either early in the morning or late in the afternoon, when the contrast between the bright rings and the sky is greatest. The structure within Earth's rings would be far more complex and detailed than they might appear from a distance. Just like Saturn's rings, which from Earth appear as smooth bands, but are actually composed of thousands of individual ringlets, gaps, and intricate structures. Earth's rings would have incredible detail when viewed through telescopes or binoculars. Amateur astronomers would have a field day observing and cataloguing the various divisions, gaps, and density variations within the ring system. The rings would also create spectacular optical effects. When the sun, Earth, and the rings align just right, observers might see ring shadows cast on Earth's surface, creating moving bands of darkness that would sweep across the landscape, like the shadows of fast-moving clouds. These shadow events would be predictable and would become major spectacles that people would travel thousands of miles to witness, similar to how people travel to see solar eclipses today. The appearance of the rings would change throughout the night as Earth rotates. Unlike the moon and stars, which appear to move across the sky due to Earth's rotation, the rings would remain fixed relative to Earth's surface. However, their illumination would change as different portions of the rings moved into and out of Earth's shadow. This would create a constantly changing light show as different sections of the rings brightened and dimmed throughout the night. Seasonal variations would add another layer of complexity to ring observations. Due to Earth's axial tilt, the angle at which sunlight hits the rings would change throughout the year. During certain seasons, the rings might appear much brighter as they receive more direct sunlight. During other seasons, they might appear dimmer, or even disappear entirely when they align edge-on with the sun, similar to how Saturn's rings occasionally appear to vanish when viewed from Earth during certain orbital alignments. The rings would also interact with Earth's aurora, the northern and southern lights. The charged particles that create auroras would likely interact with ring particles near Earth's magnetic poles, potentially creating spectacular displays where the aurora and rings would appear together in the same sky. Imagine seeing the dancing green curtains of the northern lights silhouetted against the bright backdrop of Earth's rings, creating a light show unlike anything currently visible on our planet. Photography of Earth's rings would become an entirely new art form. The rings would be bright enough to photograph with ordinary cameras, but their enormous scale would require wide-angle lenses to capture their full extent. Time-lapse photography would reveal the subtle changes in ring illumination throughout the night, while long-exposure photography might capture details in the ring structure invisible to the naked eye. Different types of ring particles would reflect light differently, creating subtle color variations and brightness patterns within the rings. Ice-rich regions might appear brighter and whiter, while rocky regions might appear darker and more reddish. These variations would create a complex tapestry of light and shadow that would change as the viewing angle and illumination conditions change throughout the day and night. The rings would also create unique meteorological effects. The partial blocking of sunlight by ring particles might create subtle temperature variations on Earth's surface, leading to unique weather patterns and cloud formations. Some regions might experience slightly cooler temperatures due to ring shadows, while other regions might be unaffected. These effects would be most pronounced in equatorial regions where the rings would appear directly overhead. For airline pilots and passengers, Earth's rings would create navigation landmarks unlike anything that exists today. Pilots could use the rings as a reference for direction and position, similar to how ancient mariners used the stars for navigation. The rings would be visible from aircraft flying above most cloud layers, providing a constant celestial reference that would never change position relative to Earth's surface. The psychological and emotional impact of seeing Earth's rings every day would be profound. Unlike our current sky, which can sometimes seem empty and distant, a ring-adorned sky would feel intimate and connected. The rings would serve as a constant reminder of Earth's place in the solar system and the dynamic forces that shape planetary environments. Every person on Earth would grow up with this spectacular celestial display as a normal part of their daily experience. So, what would Earth's rings actually look like from our planet's surface? They would be the most spectacular, beautiful, and awe-inspiring sight in our sky, visible to nearly everyone on Earth, but appearing completely different depending on where you happen to live. They would transform our planet into a world of constant celestial wonder, where looking up would never again be ordinary or boring. The rings would be dynamic, changing, and absolutely magnificent, making Earth one of the most beautiful planets in the entire solar system. The question of whether Earth's rings could actually change our planet's climate opens up one of the most fascinating and complex areas of planetary science. While the rings would undoubtedly be spectacular to look at, their influence on Earth's weather patterns and global climate system could be far more profound and far-reaching than most people might imagine. The answer isn't simply yes or no, but rather an intricate story of how cosmic mechanics intersect with atmospheric science to create effects that could ripple through every aspect of life on our planet. To understand how rings might affect Earth's climate, we need to think about the fundamental driver of all weather and climate on our planet, the Sun. Every day, our Sun delivers approximately 1,366 watts of energy per square meter to the top of Earth's atmosphere. This solar energy powers everything from ocean currents and wind patterns to the water cycle and photosynthesis. Any significant interruption or modification of this energy flow would inevitably have consequences for Earth's climate system. Earth's rings would act like a partially transparent umbrella, occasionally blocking some of this crucial solar energy from reaching our planet's surface. The amount of energy blocked would depend on several factors, including the density of the ring system, the size and composition of ring particles, and most importantly, the geometry of how Earth, the rings, and the Sun align throughout our planet's daily rotation and yearly orbit. The most dramatic climate effects would occur in equatorial regions, where the rings would appear directly overhead. As Earth rotates on its axis every 24 hours, different portions of the equatorial zone would pass through ring shadows, creating alternating periods of normal sunlight and reduced solar radiation. These shadow events wouldn't be like the brief darkness of a solar eclipse, but rather like having intermittent cloud cover that follows predictable patterns based on ring structure and density. Computer climate models developed by NASA and other research institutions have explored exactly this scenario. When scientists input hypothetical Earth ring systems into their sophisticated climate simulation programs, the results reveal a complex web of interconnected effects that cascade through Earth's entire atmospheric system. The primary effect is regional cooling in areas that experience frequent ring shadows, but the secondary effects are where things get really interesting and complicated. Equatorial regions currently receive the most direct and intense solar radiation on Earth, making them the warmest areas of our planet. This intense heating drives the formation of the Intertropical Convergence Zone, a band of rising air near the equator that creates much of the world's rainfall and helps drive global atmospheric circulation patterns. If rings were to reduce solar heating in equatorial regions, even by just a few %, it could significantly alter these crucial atmospheric circulation patterns. The changes wouldn't stop at just local temperature variations. Earth's climate system is interconnected in ways that scientists are still working to fully understand. Ocean currents, for example, are driven largely by temperature differences between different regions of the planet. If rings were to cool equatorial regions while leaving polar regions unaffected, the temperature gradient between equator and poles would decrease. This could slow down major ocean currents like the Gulf Stream, which carries warm water from the tropics toward Europe and helps keep countries like Britain much warmer than their latitude would otherwise suggest. Monsoon patterns, which billions of people depend on for agriculture and fresh water, could also be affected by ring-induced climate changes. Monsoons are driven by seasonal temperature differences between land and ocean, and by the movement of the Intertropical Convergence Zone throughout the year. Ring shadows that consistently affect certain land areas could alter these temperature patterns enough to shift monsoon timing, intensity, or geographic extent. The implications for agriculture and water resources could be enormous. The seasonal variation in ring effects would add another layer of complexity to climate impacts. Due to Earth's axial tilt, the angle at which sunlight hits the rings would change throughout the year. During some seasons, the rings might cast more pronounced shadows, while during others, the shadows might be minimal or absent entirely. This would create a new type of seasonal variation superimposed on top of Earth's existing seasonal patterns caused by axial tilt. Interestingly, not all climate effects from rings would necessarily be negative or cooling. In some regions and under certain conditions, rings might actually cause local warming. This could happen through a process similar to how clouds can sometimes trap heat radiated from Earth's surface, preventing it from escaping to space. Ring particles could potentially absorb some of the infrared radiation emitted by Earth and re-radiate it back downward, creating a localized greenhouse effect in certain areas. The composition of ring particles would play a crucial role in determining climate effects. If Earth's rings were composed primarily of highly reflective ice particles, like Saturn's rings, they would reflect most sunlight back to space, creating a net cooling effect. However, if the rings contain significant amounts of darker, rocky material, they might absorb more solar energy and re-radiate it as heat, potentially creating more complex heating and cooling patterns. Atmospheric scientists have identified several specific mechanisms through which rings could affect Earth's climate system. Solar radiation modification would be the most direct effect, but rings could also influence atmospheric chemistry, cloud formation patterns, and even the planet's radiation budget, the balance between incoming solar energy and outgoing heat radiation that ultimately determines Earth's temperature. Cloud formation could be particularly affected by ring-induced climate changes. Clouds form when air masses with different temperatures and humidity levels interact, and rings could create new patterns of atmospheric heating and cooling that would alter where and when clouds develop. Some regions might experience increased cloud formation due to changing air circulation patterns, while others might see decreased cloudiness. Since clouds themselves have a major impact on climate, by reflecting sunlight and trapping heat, these changes could amplify or moderate the direct effects of ring shadows. The altitude at which Earth's rings would exist, roughly 2,000 to 12,000 kilometers above the surface, would place them well above Earth's atmosphere but still within the region where they could cast shadows on the surface. This is actually the ideal altitude for maximum climate impact, high enough to avoid atmospheric interference, but low enough to create significant shadowing effects. Regional climate variations would be one of the most noticeable effects for people living on Earth. Some areas might experience cooler summers due to ring shadows, while others might have milder winters due to altered atmospheric circulation patterns. Coastal regions might see changes in sea breeze patterns, while mountainous areas could experience different precipitation patterns due to modified airflow around topographic features. Agricultural implications of a ring-induced climate change could be substantial. Many crops are sensitive to small changes in temperature, rainfall, and sunlight patterns. Regions that currently enjoy optimal growing conditions might become less suitable for certain crops, while other areas might become more favorable. The timing of seasonal changes could shift, affecting planting and harvesting schedules that have been optimized over centuries of agricultural development. The impact on Earth's ice caps and glaciers would depend on the overall magnitude of climate change caused by the rings. If rings created significant global cooling, it could potentially slow down or even reverse some of the ice melting currently occurring due to global warming from greenhouse gas emissions. Conversely, if rings caused regional warming in polar areas through altered atmospheric circulation, ice melting could accelerate in those regions. Ocean temperatures would also respond to ring-induced climate changes. Cooler surface waters in some regions could affect marine ecosystems, fish populations, and ocean chemical processes. The ocean's ability to absorb carbon dioxide from the atmosphere is temperature dependent, so ring-related temperature changes could even affect the global carbon cycle and atmospheric carbon dioxide levels. Weather prediction would become significantly more complex in a world with rings. Current weather forecasting models would need to be completely redesigned to account for the additional variable of ring shadows and their effects on atmospheric heating patterns. Meteorologists would need to develop new techniques for predicting not just traditional weather patterns, but also the interaction between ring shadows and atmospheric conditions. The psychological and social effects of ring-induced climate changes could be as significant as the physical effects. Human societies have adapted over thousands of years to Earth's current climate patterns, and any significant changes would require major adaptations in agriculture, architecture, urban planning, and daily life. The predictable nature of ring shadows might actually make adaptation easier than adapting to random climate variations, since ring shadow patterns would follow precise mathematical relationships based on orbital mechanics. Climate research would be revolutionized by the presence of rings. Scientists would have a natural laboratory for studying how changes in solar radiation affect climate systems. The precise, predictable nature of ring shadows would allow researchers to separate ring-induced climate effects from other climate variables in ways that are currently impossible with Earth's existing climate system. International climate agreements and policies would need to account for ring-induced climate effects. If rings caused significant regional climate variations, some countries might benefit while others suffered, creating new types of international tensions and cooperation needs around climate adaptation and mitigation strategies. So could Earth's rings actually change our planet's climate? The scientific evidence suggests that yes, they absolutely could, and in ways that would be both profound and complex. The effects wouldn't necessarily be catastrophic, but they would be real, measurable, and would require human civilization to adapt to a new set of climate realities. The rings would essentially add a new layer of complexity to Earth's climate system, creating opportunities for both beneficial and challenging changes that would reshape how we think about weather, agriculture, and our relationship with the cosmic forces that shape our world. Throughout human history, no celestial phenomenon has shaped our cultures, religions, mythologies, and daily lives more profoundly than the objects we see in the sky above us. The sun governs our days, the moon marks our months, and the stars have guided everything from navigation to agricultural timing to spiritual beliefs for thousands of years. If Earth suddenly acquired magnificent rings like Saturn, the cultural transformation would be so profound and far-reaching that it would fundamentally reshape human civilization in ways we can barely begin to imagine. The most immediate and obvious impact would be on human timekeeping and calendar systems. Our current calendars are based entirely on the predictable cycles of the sun and moon, but Earth's rings would introduce an entirely new celestial reference system that would be impossible to ignore. The rings would remain fixed relative to Earth's surface, unlike the sun, moon and stars, which appear to move across the sky due to Earth's rotation and orbit. This unique property would make the rings the ultimate cosmic landmark, a permanent feature that could serve as a reference point for navigation, architecture, and timekeeping, unlike anything that has ever existed in human experience. Ancient civilizations would have undoubtedly built their entire understanding of the cosmos around the presence of rings. Imagine how different the pyramids of Egypt might have been if their builders had been able to use the rings as a permanent celestial reference. Instead of aligning with stars that slowly shift position over centuries due to precession, ancient architects could have aligned their monuments with the unchanging geometry of the ring system. The great stone circles like Stonehenge might have been oriented to frame specific views of the rings rather than tracking the movements of the sun and moon. Religious and spiritual implications would be absolutely enormous. Every major religion on Earth has incorporated celestial observations into its theology and practice. The rings would become central to religious imagery, symbolism, and doctrine in ways that would vary dramatically between different cultures and belief systems. Some religions might interpret the rings as a divine bridge connecting Earth to the heavens, while others might see them as a protective barrier placed around Earth by benevolent deities. The perfectly circular, eternal nature of the rings would likely inspire countless theological interpretations about cycles, eternity, and the relationship between the earthly and divine realms. Mythology and folklore would be completely transformed by the presence of rings. Instead of creating stories about why the moon has phases or why the sun rises and sets, human cultures would develop elaborate mythologies to explain the origin and meaning of the magnificent ring system stretching across their skies. Different cultures would undoubtedly create vastly different explanations. Some might envision the rings as the remnants of a cosmic battle between gods, while others might see them as a celestial river or pathway for souls traveling between worlds. The impact on art and literature would be revolutionary. Painters, sculptors, poets, and writers would have an entirely new source of inspiration dominating their creative landscape. The rings would appear in countless works of art, not just as background elements, but as central themes representing everything from divine protection to cosmic beauty to the interconnectedness of all things. The way rings appear differently from different latitudes would create distinct regional artistic traditions, with equatorial cultures developing completely different ring-based artistic themes than temperate or polar cultures. Navigation systems would be fundamentally transformed by the presence of rings. Current navigation relies on the sun, moon, stars, and magnetic compass directions, but rings would provide a new type of reference that combines the best features of celestial and terrestrial navigation. Since rings remain fixed relative to Earth's surface, they would serve as perfect directional indicators that never change position. Sailors could use the rings to determine their latitude with unprecedented precision, while land-based travelers could use ring positions to maintain accurate direction, even in unfamiliar territory. Architecture and urban planning would inevitably incorporate ring alignments into building design and city layouts. Just as many ancient and modern buildings are oriented to take advantage of solar angles for heating and lighting, buildings in a ring-adorned world would be designed to optimize views of the ring system. Cities might be laid out with major streets and plazas aligned to frame spectacular views of the rings. creating urban landscapes that are inherently connected to the cosmic display overhead. The development of astronomy and mathematics would be accelerated by the presence of rings. Ancient astronomers would have had a perfect natural laboratory for studying orbital mechanics, gravitational effects, and celestial geometry right in their own sky. The complex structure of rings with their gaps, divisions, and varying densities would have provided early scientists with observable examples of mathematical relationships and physical principles that took human civilization centuries to discover through other means. Educational systems would be transformed by having such a spectacular and accessible example of cosmic phenomena visible every day. Children would grow up with an intuitive understanding of concepts like orbital mechanics, gravitational effects, and planetary science that currently require advanced education to comprehend. The rings would serve as a natural teaching tool for everything from basic geometry to advanced astrophysics, making scientific education more concrete and visually engaging. Cultural celebrations and festivals would inevitably develop around ring-related phenomena. Just as many cultures have festivals celebrating solstices, equinoxes, eclipses, and lunar phases, ring cultures would create celebrations around ring shadow events, optimal ring viewing times, and seasonal changes in ring appearance. These festivals would likely become some of the most spectacular and widely celebrated events in human culture, bringing together astronomy, art, music, and community celebration in unique ways. The impact on human psychology and philosophy would be profound. Living under a sky dominated by such a magnificent and obviously artificial-looking structure would constantly remind humans of their place in a larger cosmic system. The rings would serve as a daily reminder that Earth is not just an isolated world, but part of a dynamic planetary system governed by physical laws that create beauty on a cosmic scale. This constant celestial reminder might make humans more aware of environmental interconnectedness and cosmic perspective in their daily lives. Different latitude regions would develop distinctly different ring cultures based on how the rings appear from their location. Equatorial cultures, where rings appear as thin lines overhead, would develop different traditions and beliefs than temperate cultures where rings appear as broad arcs across the sky. Polar cultures, where rings are barely visible or invisible, might develop entirely different cultural relationships with the cosmic display that dominates life in other parts of the world. Language and communication would be enriched by ring-related terminology and metaphors. Just as current languages are filled with references to the sun, moon, and stars, ring cultures would develop extensive vocabularies for describing ring phenomena, appearances, and relationships. Metaphors based on ring imagery would become common in poetry, literature, and daily conversation. People might describe stable relationships as being as permanent as the rings, or use ring terminology to describe concepts of unity, protection, and cosmic connection. Marriage and romantic traditions would likely incorporate ring symbolism in ways that go far beyond our current use of wedding rings. The cosmic rings overhead might inspire new types of marriage ceremonies, anniversary celebrations, and romantic traditions. Couples might time their weddings to coincide with spectacular ring displays, or exchange vows under particularly beautiful ring configurations. Scientific and technological development would be accelerated by the constant presence of such an obvious example of complex orbital mechanics. Cultures would be motivated to develop better telescopes, mathematical tools, and scientific instruments to study and understand the ring system. This technological development might accelerate the advancement of human civilization by centuries, as the daily presence of rings would provide constant motivation and opportunity for scientific discovery. Trade and commerce would be affected by ring-related navigation advantages and cultural preferences. Societies with better ring-based navigation systems might gain advantages in exploration and trade. Cultural artifacts, artwork, and goods featuring ring themes would become valuable trade items between different regions with varying ring visibility. Military and defense strategies would incorporate ring-based advantages. Armies could use ring positions for navigation and coordination in ways that would be impossible with current celestial references. The permanent nature of ring positions would allow for more precise military planning and coordination than current systems allow. Social hierarchies might develop around ring knowledge and interpretation. Priests, astronomers, and scholars who understood ring phenomena might gain special status in their societies. The ability to predict ring shadows, explain ring behavior, or create accurate ring calendars could become sources of power and influence, similar to how eclipse prediction gave ancient astronomers special status. International relations and cultural exchange would be influenced by the shared experience of living under the same ring system. Despite appearing different from various latitudes, the rings would still be a common human experience that could serve as a unifying cultural reference point. International cooperation in ring research and observation might develop into one of humanity's first truly global scientific enterprises. The preservation of cultural knowledge would be enhanced by having such a stable, celestial reference system. Unlike stars, which slowly change position over centuries, ring positions would remain constant, allowing cultural knowledge and traditions to be preserved with greater accuracy across generations. Stories, legends, and historical records that reference ring positions would remain accurate and meaningful for much longer periods than current celestial references allow. So how would Earth's rings affect human culture? They would transform virtually every aspect of human civilization, from our most basic systems of timekeeping and navigation to our highest expressions of art, philosophy, and spiritual belief. The rings would not just be something beautiful to look at. They would become the foundation for entirely new ways of understanding our place in the cosmos, organizing our societies, and expressing our deepest cultural values. Human culture would be as fundamentally shaped by the presence of rings as it has been by the presence of the sun and moon, creating a civilization that would be recognizably human, yet completely different from anything that has ever existed on our ringless world. While Earth's rings would create breathtaking beauty in our skies and profoundly impact human culture, they would also present some of the most dangerous and challenging obstacles to space exploration that human civilization has ever faced. The dream of reaching the stars would suddenly become a deadly obstacle course through a cosmic minefield that makes our current space debris problems look trivial by comparison. Understanding these challenges requires diving deep into the harsh realities of orbital mechanics, where even the smallest particles become devastating projectiles capable of destroying spacecraft and ending human lives. The fundamental problem with rings is that they represent millions or billions of objects orbiting Earth at tremendous speeds. Ring particles at the inner edge of Earth's hypothetical ring system, roughly 2,000 kilometers above our planet's surface, would be traveling at approximately 7.8 kilometers per second. That's over 28,000 kilometers per hour, fast enough to circle the entire Earth in about 90 minutes. At these incredible velocities, even the tiniest ring particle becomes a devastating projectile with kinetic energy far exceeding that of a high-powered rifle bullet. To put this danger in perspective, consider that current space agencies like NASA and the European Space Agency already spend enormous resources tracking and avoiding space debris much smaller and less dense than what Earth's rings would contain. The International Space Station regularly has to perform debris avoidance maneuvers to dodge pieces of defunct satellites, spent rocket stages, and other orbital junk. These debris objects are scattered randomly throughout Earth's orbital space. But rings would represent a concentrated band of debris that spacecraft would have to cross to reach higher orbits. The challenge of launching rockets through Earth's rings would be absolutely daunting. Current rocket launches follow carefully planned trajectories that take spacecraft from Earth's surface through progressively higher orbits until they reach their intended destination. Most satellites destined for geostationary orbit, including crucial communication and weather satellites, follow paths that would take them directly through the ring zone. This means that every single launch to high Earth orbit would require threading the needle through a cosmic shooting gallery where collision with even microscopic particles could be catastrophic. The physics of these high-speed collisions is sobering. When objects collide at orbital velocities, the kinetic energy involved is enormous. A ring particle the size of a marble, weighing perhaps 10 grams, traveling at 7 kilometers per second, would have the kinetic energy equivalent to a small hand grenade. A particle the size of a golf ball would carry energy comparable to a stick of dynamite. These aren't theoretical concerns, but real physics that spacecraft engineers would have to account for in every mission design. Current spacecraft are designed with some protection against micrometeorite impacts, but ring particles would represent a threat orders of magnitude greater than anything spacecraft currently face. The Whipple shields used on the International Space Station, which consist of multiple layers of material designed to break up and absorb incoming particles, would be inadequate against the size and density of particles that rings would contain. Spacecraft would need entirely new types of armor and protection systems, making them much heavier and more expensive to launch. The navigation challenges would be equally daunting. Spacecraft guidance systems would need to be completely redesigned to account for the gravitational effects of ring particles. While individual particles would have negligible gravitational influence, the collective gravitational effect of billions of particles would create subtle but measurable perturbations in spacecraft orbits. Mission planners would need detailed maps of ring density and particle distribution to calculate accurate trajectories, and these maps would need constant updating as the ring system evolved over time. Communication satellites would face perhaps the greatest challenges of all. Most of our crucial communication infrastructure, including television broadcasting, internet backbone connections, and GPS navigation systems, depends on satellites in geostationary orbit at 35,800 kilometers altitude. To reach these orbits, satellites must pass through the ring zone, and once in position, they would need to operate in an environment where ring particles occasionally migrate to higher orbits due to gravitational perturbations. The economic implications would be staggering. Current satellite launches already cost hundreds of millions of dollars, but ring-related challenges would likely increase these costs by factors of 10 or more. The additional shielding, navigation systems, and mission complexity required to safely navigate through rings would make space access prohibitively expensive for many applications. The commercial space industry, which has been driving down launch costs through reusable rockets and innovative technologies, would face enormous new barriers to cost reduction. Polar orbits would become the preferred path for many space missions. Since rings lie in Earth's equatorial plane, spacecraft following polar or highly inclined orbits would spend less time in the dense ring regions. This would favor certain types of missions, such as Earth observation satellites that benefit from polar orbits anyway, but would make equatorial missions much more difficult and expensive. The International Space Station, which currently follows an inclined orbit that takes it through equatorial regions, would need to be redesigned or relocated to avoid ring hazards. Space tourism, an industry just beginning to develop, would face enormous safety challenges. Current space tourism ventures, like those planned by companies such as SpaceX and Blue Origin, assume relatively safe access to low Earth orbit, but rings would make these missions far more dangerous. The additional safety systems and mission complexity required to protect tourists from ring particle impacts would likely make space tourism economically unfeasible for decades or centuries. Robotic space missions would also be severely impacted. Current Mars rovers, asteroid missions, and planetary exploration spacecraft follow trajectories that take them through various regions of Earth's orbital space before heading to their destinations. These missions would need complete redesign to avoid ring hazards, likely requiring more complex trajectories that consume more fuel and take longer to reach their targets. Some missions might become impossible due to the inability to safely navigate through the ring system. The development of new propulsion technologies would become a critical priority. Current chemical rockets, which provide high thrust for relatively short periods, would be poorly suited for the careful maneuvering required to navigate through rings. Ion drives and other low-thrust, high-efficiency propulsion systems would become essential for spacecraft that need to make precise course corrections while traveling through ring regions. This would accelerate the development of advanced propulsion technologies, but at enormous cost and complexity. Space debris mitigation would become even more critical than it already is. Current international agreements require spacecraft operators to limit the creation of new space debris. But in a ring environment, any new debris created by spacecraft operations or collisions would add to an already dangerous situation. The Kessler syndrome, a theoretical cascade where collisions create more debris that causes more collisions, would be much more likely to occur in ring regions where particle density is already high. International cooperation in space exploration would become absolutely essential. The challenges of navigating through rings would be too great for any single nation to solve alone. Countries would need to share detailed ring observations, coordinate mission planning to avoid creating additional hazards, and develop common safety standards for ring transit. This could accelerate international space cooperation, but might also create new sources of conflict if nations disagree on access rights or safety protocols. The timeline for human space exploration would be dramatically extended. Current plans for returning humans to the Moon, establishing lunar bases, and eventually sending astronauts to Mars assume relatively straightforward access to Earth orbit and beyond. Ring hazards would add years or decades to mission development timelines, as engineers develop new safety systems and test procedures for safely transiting ring regions. The dream of becoming a spacefaring civilization would face its greatest obstacle yet. Research and development costs would skyrocket as space agencies and private companies work to solve ring-related challenges. New materials would need to be developed for spacecraft shielding. New guidance systems would need to be created for navigation through particle fields, and entirely new mission architectures would need to be designed. The total cost of overcoming ring-related obstacles might exceed the entire current global space budget by orders of magnitude. Emergency response and rescue operations would become far more complex. Current space rescue scenarios, such as evacuating astronauts from the International Space Station, assume relatively quick and direct access routes. Ring hazards would make emergency missions much more dangerous and time-consuming, potentially making some types of space rescue impossible. This would require fundamental changes in how human space missions are planned and executed. Long-term space infrastructure development would be severely hampered. Current visions of space manufacturing, orbital colonies, and large-scale space construction all depend on routine, affordable access to various Earth orbits. Ring hazards would make such infrastructure development prohibitively expensive and dangerous, potentially delaying the development of space-based civilization by centuries. However, the challenges would also drive innovation in unprecedented ways. The urgent need to solve ring-related problems would accelerate the development of new technologies, materials, and techniques that might have applications far beyond space exploration. Advanced particle shielding might lead to better radiation protection for terrestrial applications. Precise navigation through particle fields might advance robotics and autonomous systems. The challenge of operating in ring environments might ultimately make human civilization more technologically capable. The psychological impact on astronauts and mission planners would be significant. Space exploration already requires enormous courage and careful risk management, but ring hazards would add entirely new categories of danger that space travelers would need to accept. The knowledge that a collision with invisible particles could instantly destroy a spacecraft would create new forms of space-related anxiety and stress that mission planners would need to address. So while Earth's rings would be beautiful and culturally transformative, they would also represent one of the greatest obstacles to human space exploration ever encountered. The dream of reaching the stars would require overcoming challenges that would test the limits of human engineering, international cooperation, and determination. Space exploration would not be impossible, but it would be far more difficult, expensive, and dangerous than anything human civilization has yet attempted. The rings would force humanity to become far more sophisticated in our approach to space technology. But they would also delay our expansion into the cosmos by generations or centuries. The question of how Earth could actually acquire a ring system like Saturn's takes us into some of the most dramatic and catastrophic scenarios that planetary science can imagine. While Earth's rings would be beautiful and scientifically fascinating, the events required to create them would be among the most violent and spectacular cosmic disasters our planet could experience. Understanding these scenarios requires exploring the extreme physics of planetary collisions, tidal disruption, and gravitational chaos that operate on scales so vast they challenge human comprehension. The most scientifically plausible scenario for Earth acquiring rings would involve what astronomers call tidal disruption, a process where gravitational forces literally tear apart large objects that venture too close to our planet. This isn't science fiction, but established physics that we observe happening throughout the solar system. The key concept is the Roche limit, that critical distance we discussed earlier, where Earth's tidal forces become stronger than the gravitational forces holding an object together. Imagine a small moon, perhaps 50 to 100 kilometers in diameter, somehow finding itself on a collision course with Earth. This could happen through gravitational perturbations from other planets, the influence of passing asteroids, or complex orbital dynamics that slowly decay the moon's orbit over millions of years. As this doomed moon approaches Earth, it would initially appear as just another bright object in our night sky, perhaps visible to amateur astronomers who might track its unusual orbital behavior. The tidal disruption process would be absolutely spectacular to witness, assuming anyone survived to observe it. As the approaching moon crossed Earth's Roche limit, roughly 18,000 kilometers from Earth's center, the differential gravitational forces would begin to overcome the moon's own gravity. The side of the moon facing Earth would experience stronger gravitational pull than the far side, creating tidal forces that would gradually stretch the moon like cosmic taffy. The disruption wouldn't happen instantly, but would unfold over hours or days, depending on the moon's size, composition, and approach velocity. Initially, the moon would begin to elongate in the direction of Earth, developing a teardrop shape as material on the Earth-facing side was pulled more strongly than material on the far side. Cracks would appear on the surface as internal stresses exceeded the strength of rock and ice. These cracks would grow and spread as tidal forces continued to increase. Eventually, the tidal forces would overcome the moon's structural integrity entirely. The moon would break apart in a cascade of destruction, starting with small pieces being torn away from the main body and gradually escalating until the entire object disintegrated into countless fragments. The largest pieces might be several kilometers across, while the smallest would be tiny particles of dust and debris. This entire debris field would continue orbiting Earth, spreading out over time to form a ring system. The energy involved in such an event would be beyond imagination. A moon 100 kilometers in diameter has a mass of roughly 1 trillion tons, and its destruction would release energy equivalent to billions of nuclear weapons. The debris shower reaching Earth's surface would create impact craters around the globe and might trigger global climate changes similar to those that ended the age of dinosaurs. The immediate aftermath would be catastrophic for life on Earth. but survivors would witness the formation of the most spectacular ring system in the inner solar system. An alternative scenario involves a massive collision between two large objects within Earth's gravitational influence. This could happen if Earth somehow acquired two small moons that gradually spiraled inward due to tidal friction, eventually colliding with each other within the ring formation zone. The collision would shatter both objects, creating a debris field that would spread out to form rings. This scenario is actually more likely than single object tidal disruption because it doesn't require a new object to approach Earth from the outer solar system. Mars provides a fascinating real-world example of how this process might work. Mars has two small moons, Phobos and Deimos, and Phobos is gradually spiraling inward due to tidal forces. In approximately 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces to form a temporary ring system around the red planet. This gives us a preview of exactly the type of process that could theoretically create rings around Earth. The capture of a passing comet or asteroid could also lead to ring formation, though this would require incredibly precise orbital mechanics. A comet approaching from the outer solar system would need to pass close enough to Earth to be captured by our planet's gravity, but not so close that it crashes into the surface. The captured object would then need to spiral inward due to atmospheric drag or tidal effects until it reaches the Roche limit and breaks apart. The odds of this happening naturally are astronomically small, but it's not physically impossible. Artificial ring creation represents a theoretically possible but practically impossible scenario given current human technology. Humans could potentially create rings by deliberately destroying objects in Earth orbit, or by launching massive amounts of material into ring-forming orbits. However, the scale of such an undertaking would be beyond anything human civilization has ever attempted. Creating rings comparable to Saturn's would require moving trillions of tons of material into specific orbits around Earth, a task that would require technology and resources far beyond current human capabilities. The composition of Earth's rings would depend entirely on what type of object was destroyed to create them. If the rings formed from a disrupted ice-rich comet, they would be primarily composed of water ice mixed with rocky dust, similar to Saturn's rings but probably containing more rocky material. If they formed from a disrupted rocky asteroid, they would be primarily composed of stone and metal, creating darker, less reflective rings than Saturn's brilliant ice rings. The timing of ring formation would be crucial for life on Earth. If rings formed during Earth's early history, before complex life evolved, the planet might have developed differently due to altered climate patterns and reduced solar radiation reaching the surface. However, if rings formed after complex ecosystems had already developed, the sudden change in solar radiation patterns could trigger mass extinction events as dramatic as any in Earth's geological history. The debris impact phase immediately following ring formation would be the most dangerous period for Earth's surface. While most of the disrupted material would remain in orbit to form rings, some debris would inevitably have orbits that intersect with Earth's atmosphere. This would create intense meteor showers lasting potentially for years or decades as ring material gradually rained down on Earth's surface. These impacts could trigger wildfires, atmospheric heating, and climate changes that would affect every ecosystem on the planet. Gravitational interactions with the Moon would play a crucial role in how Earth's rings would form and evolve. The Moon's powerful gravitational influence would help shape the ring system, creating gaps and divisions similar to those found in Saturn's rings. However, the Moon would also gradually remove ring material through resonant interactions, meaning that Earth's rings would be temporary features lasting perhaps thousands to millions of years rather than the hundreds of millions of years that Saturn's rings have persisted. The probability of Earth naturally acquiring rings in the near future is extremely low. Our planet currently has no small moons or captured asteroids that could serve as ring-forming material. The asteroid belt lies too far away for objects to be easily perturbed into Earth-crossing orbits, and most near-Earth asteroids are too small to create substantial ring systems, even if they were disrupted. The formation of Earth's rings would likely require some extraordinary event or cosmic coincidence that occurs perhaps once in hundreds of millions of years. Historical evidence suggests that Earth might have had rings in the distant past. Some scientists theorize that the giant impact event that created our moon about 4.5 billion years ago might have temporarily created a debris disk around Earth. This disk would have gradually coalesced to form the moon we see today. But for a brief period in Earth's early history, our planet might have been surrounded by a spectacular ring system formed from the debris of planetary collision. The search for ring-forming objects continues through astronomical surveys that track near-Earth asteroids and comets. Programs like the Near-Earth Object Observations Program constantly monitor space for objects that might pose collision risks to Earth. While these programs are primarily focused on planetary defense, they also provide the data needed to identify objects that might theoretically be captured and disrupted to form rings, though such scenarios remain highly speculative. Future technological developments might eventually make artificial ring creation feasible, though this would represent one of the most ambitious engineering projects ever conceived. Advanced space mining operations might be able to capture and redirect asteroids into Earth orbit, while new propulsion technologies could provide the precise orbital control needed to place ring material in stable configurations. However, such capabilities would require technological advances that are currently decades or centuries beyond human reach. The study of ring formation around other planets provides valuable insights into how Earth might acquire rings. Observations of ring systems around Jupiter, Saturn, Uranus, and Neptune reveal the complex gravitational dynamics and material transport processes that create and maintain planetary rings. These observations help scientists understand the conditions required for ring formation and the factors that determine ring longevity and structure. Computer simulations of hypothetical Earth ring formation scenarios allow scientists to explore the physics of tidal disruption and debris evolution in Earth's gravitational environment. These simulations reveal the complex interplay between gravitational forces, orbital mechanics, and collision dynamics that would shape Earth's rings. The results show that while ring formation is possible, it would require extraordinary circumstances that are unlikely to occur naturally in the near future. So how could Earth actually acquire rings? The most realistic scenarios involve catastrophic events like tidal disruption of approaching objects, or collisions between captured bodies within Earth's gravitational influence. These events would be rare, violent, and potentially devastating for life on Earth, but they would also create one of the most spectacular displays in the solar system. While the probability of such events occurring naturally is extremely low, they remain within the realm of physical possibility, making Earth's rings a fascinating topic for both scientific study and speculative imagination. The formation of Earth's rings would represent one of the most dramatic and transformative events in our planet's history, fundamentally changing both the appearance of our world and the conditions for life on its surface. The presence of Earth's rings would create biological and evolutionary pressures unlike anything life on our planet has ever experienced. While the immediate formation of rings might cause short-term catastrophic effects, the long-term presence of a ring system would fundamentally alter the evolutionary trajectory of every species on Earth in ways both subtle and profound. Understanding these effects requires exploring how life responds to changes in light patterns, climate variations, and environmental pressures that would be entirely unique to a ring-adorned world. The most immediate biological impact would come from the altered light and shadow patterns that rings would create across Earth's surface. Life on Earth has evolved over billions of years under the assumption that sunlight arrives in predictable daily and seasonal patterns. plants have optimized their photosynthesis processes for consistent light availability. Animals have developed circadian rhythms based on regular day-night cycles, and entire ecosystems have synchronized their activities around solar patterns that have remained essentially unchanged throughout evolutionary history. Earth's rings would disrupt these ancient patterns by creating intermittent shadows that would sweep across the planet's surface in complex, predictable patterns. Unlike clouds, which create random and temporary shade, ring shadows would follow precise mathematical relationships based on Earth's rotation, orbital position, and ring structure. These shadows wouldn't be brief like solar eclipses, but could last for minutes or hours as different sections of the ring system pass between the Sun and various regions of Earth's surface. Plant life would face the most immediate evolutionary pressure from these changing light conditions. Photosynthesis, the fundamental process that powers most life on Earth, depends on consistent access to sunlight. Plants in regions that experienced frequent ring shadows would need to adapt by developing more efficient photosynthetic processes, larger leaf surfaces to capture available light, or energy storage systems to sustain themselves during shadow periods. Over evolutionary timescales, this could lead to the development of entirely new photosynthetic strategies and plant architectures. Different plant species would respond to ring shadows in dramatically different ways. Some plants might develop the ability to rapidly adjust their leaf orientation to track available sunlight as it shifts due to ring shadows, similar to how sunflowers currently track the sun's movement across the sky. Other plants might evolve to become more efficient at using the scattered light that would still be available during ring shadow events, developing enhanced sensitivity to indirect illumination. The seasonal variation in ring shadow patterns would add another layer of complexity to plant evolution. As Earth's axial tilt changes the angle of sunlight hitting the rings throughout the year, different regions would experience varying intensities of ring shadowing during different seasons. Plants would need to adapt not just to the immediate effects of ring shadows, but to the seasonal patterns of how those shadows change throughout the year. Animal evolution would be equally affected by the presence of rings, though in more complex and interconnected ways. Many animals have evolved circadian rhythms that depend on consistent light-dark cycles to regulate everything from sleep patterns to reproduction timing to migration behavior. Ring shadows would create additional periods of darkness or reduced light that could disrupt these biological clocks, forcing animals to evolve new strategies for timing their daily activities. Nocturnal animals might actually benefit from ring-related changes in light patterns. Many species that are active at night have evolved to avoid daylight predators and competition with diurnal species. Ring shadows that create additional periods of reduced light could provide new opportunities for nocturnal species to extend their active periods or expand into new ecological niches previously dominated by day-active animals. Predator-prey relationships would undergo significant evolutionary changes due to altered visibility conditions. Ring shadows would create periods when visual predators like hawks, eagles, and big cats might have reduced hunting effectiveness, while prey species might gain temporary advantages during shadow periods. Over evolutionary time, this could lead to new hunting strategies, improved night vision capabilities, or changes in activity patterns that optimize survival under variable lighting conditions. Migration patterns of birds, insects, and marine animals would be affected by the navigation challenges that rings would create. Many species rely on celestial navigation using the sun, moon, and stars to guide long-distance migrations. The presence of bright, permanent ring structures in the sky would provide new navigation references, but would also potentially interfere with existing navigation systems that have evolved over millions of years. Some species might evolve to use ring positions as navigation aids, while others might need to develop alternative navigation strategies. Reproductive cycles of many species are triggered by specific light conditions and seasonal changes. Ring shadows could disrupt these triggers, forcing species to evolve new reproductive timing mechanisms or face reduced reproductive success. Species that breed based on day length, lunar cycles, or seasonal light variations might need to develop more flexible reproductive strategies that can accommodate the additional variability introduced by ring shadows. Marine ecosystems would experience unique evolutionary pressures from ring effects. Ocean productivity depends heavily on photosynthesis by phytoplankton, the microscopic organisms that form the base of marine food webs. Ring shadows passing over ocean surfaces could reduce photosynthetic activity in surface waters, potentially affecting the entire marine food chain. Marine species might evolve to take advantage of the predictable nature of ring shadows, timing feeding, or reproductive activities to coincide with optimal light conditions. The vertical migration patterns of marine organisms might be altered by ring shadows. Many ocean species migrate vertically through the water column on daily cycles, rising toward the surface at night to feed and descending to deeper waters during the day to avoid predators. Ring shadows that create additional periods of reduced surface light might trigger these migration patterns at unexpected times, potentially disrupting marine ecosystems and forcing evolutionary adaptations. Pollination relationships between plants and insects would face new challenges and opportunities. Many flowering plants time their blooming to coincide with peak activity periods of their insect pollinators, which are often triggered by specific light conditions. Ring shadows could disrupt these synchronized relationships, forcing both plants and pollinators to evolve more flexible timing mechanisms or develop new communication strategies to maintain effective pollination relationships. The evolution of vision systems would be accelerated by the variable light conditions created by rings. Species might evolve enhanced low-light vision capabilities to maintain visual effectiveness during ring shadow periods. Alternatively, some species might develop improved motion detection or contrast sensitivity to better detect predators or prey under changing light conditions. The evolutionary pressure to maintain visual effectiveness under variable lighting could drive rapid improvements in animal vision systems. Behavioral adaptations would likely evolve much more rapidly than physical changes. Animals are remarkably adaptable in their behavior, and many species might quickly learn to modify their activity patterns to take advantage of or avoid ring shadow effects. These behavioral changes could eventually become genetically encoded if they provide consistent survival advantages over many generations. Temperature regulation strategies would need to evolve to accommodate the thermal effects of ring shadows. Many species rely on behavioral thermoregulation, moving between sunny and shaded areas to maintain optimal body temperatures. Ring shadows would create additional cool zones that could be utilized for temperature regulation, but would also require species to develop more sophisticated thermoregulatory behaviors to track changing thermal conditions. Plant flowering and fruiting cycles might evolve to take advantage of ring shadow patterns. Some plants might time their reproductive activities to coincide with periods of reduced ring shadowing, ensuring maximum energy availability during critical reproductive phases. Other plants might evolve to use ring shadows as cues for timing reproductive activities, similar to how some current species use day length or temperature changes as seasonal indicators. The development of new ecological niches would be one of the most fascinating aspects of evolution in a ring environment. Ring shadows would create microenvironments with unique light, temperature, and humidity characteristics that don't currently exist on Earth. Species might evolve to specialize in these new ecological niches, potentially leading to rapid speciation and the development of entirely new types of ecosystems. Symbiotic relationships between species might evolve new forms under ring conditions. Plants and their mycorrhizal fungi partners might develop enhanced cooperation strategies to share resources during ring shadow periods. Animal species might evolve new forms of cooperative behavior to take advantage of the predictable nature of ring shadows for hunting, foraging, or predator avoidance. The genetic diversity of species might be affected by the environmental variability that rings would create. Species experiencing frequent ring shadows might maintain higher genetic diversity to cope with variable environmental conditions, while species in regions with minimal ring effects might experience reduced selection pressure for genetic adaptability. This could lead to interesting patterns of genetic variation across different geographic regions. Evolutionary timescales for adaptation to ring conditions would vary dramatically between different types of organisms. Microorganisms with short generation times might adapt to ring conditions within decades or centuries, while large mammals with long generation times might require thousands or millions of years to show significant evolutionary changes. This difference in adaptation rates could create temporary ecological imbalances as ecosystems adjust to ring conditions at different speeds. The fossil record would provide fascinating evidence of how life adapted to ring conditions over evolutionary time. Paleontologists studying a ring-adorned Earth might find evidence of rapid evolutionary changes in plant leaf structures, animal vision systems, and behavioral adaptations that coincided with the formation of Earth's ring system. These changes would provide valuable insights into how life responds to novel environmental pressures. Conservation biology would face entirely new challenges in a world with rings. Species that evolved under current light conditions might struggle to adapt to ring shadows, potentially requiring human intervention to prevent extinctions. Conservation strategies would need to account for the varying effects of rings on different species and ecosystems, prioritizing protection for species most vulnerable to ring-related environmental changes. So would rings have biological and evolutionary effects on Earth's life forms? Absolutely. And these effects would be both immediate and long-lasting. While the changes might be subtle compared to major extinction events, they would touch every aspect of life on Earth, from the microscopic processes of photosynthesis to the complex behaviors of the largest animals. The result would be a world where life has adapted to take advantage of the unique conditions created by Earth's ring system, creating ecosystems and evolutionary trajectories that would be impossible on any ringless planet. The presence of rings would make Earth not just more beautiful, but biologically more diverse and evolutionarily more dynamic than our current ringless world. The question of why Earth doesn't currently have rings like Saturn opens up one of the most fascinating stories in planetary science, involving ancient cosmic catastrophes, gravitational mechanics, and the unique evolutionary history that has shaped our planet's current appearance. Understanding why Earth lacks rings requires exploring the complex interplay of forces that have prevented ring formation and the specific circumstances that make our planet fundamentally different from the gas giants that do possess magnificent ring systems. The most important factor preventing Earth from having rings is the gravitational influence of our unusually large moon. When we compare Earth to other planets in our solar system, one of the most striking differences is the relative size of our moon compared to our planet. Earth's moon has a diameter roughly 1/4 that of Earth itself, making the Earth-Moon system more like a double planet than a typical planet-moon relationship. This enormous lunar companion creates gravitational effects that make long-term ring stability virtually impossible. Our moon's gravitational influence extends far beyond what most people realize. The same tidal forces that create ocean tides on Earth's surface also affect any objects orbiting in Earth's vicinity. These tidal forces, combined with gravitational resonances, create what astronomers call orbital clearing mechanisms that gradually remove particles from potential ring-forming regions around Earth. Any material that might naturally accumulate to form rings would be systematically perturbed by lunar gravity until it either crashed into Earth, escaped into space, or was captured by the moon itself. The mathematical physics behind this process involves what are called mean motion resonances, orbital relationships where objects in certain locations around Earth would be repeatedly influenced by the Moon's gravity at specific points in their orbits. These repeated gravitational tugs would gradually change the orbits of ring particles, making them either more elliptical or more inclined until they could no longer maintain stable ring configurations. The Moon essentially acts like a cosmic vacuum cleaner, slowly but persistently removing any material that might try to form rings around Earth. This lunar clearing mechanism is incredibly efficient over long time periods. Computer simulations show that even if Earth somehow acquired a dense ring system today, lunar perturbations would remove most of the ring material within thousands to millions of years. The process wouldn't be immediately obvious to human observers, but over geological timescales, it would be relentless and complete. This is fundamentally different from Saturn, whose multiple smaller moons actually help maintain ring stability through complex gravitational shepherding effects. The Sun's gravitational influence adds another layer of complexity to Earth's ring prevention system. Because Earth orbits much closer to the Sun than Saturn, solar gravitational effects on potential ring particles would be much stronger and more disruptive. The Sun creates additional resonances and perturbations that make ring stability even more challenging. Solar radiation pressure, the actual physical force of sunlight pushing on small particles, would also be stronger at Earth's distance from the Sun, gradually removing smaller ring particles through a process called the Poynting-Robertson effect. Earth's location in the inner solar system creates a fundamentally different gravitational environment than the outer solar system where Saturn resides. The inner solar system is a much more chaotic and dynamic place, with stronger tidal forces from the Sun and more frequent gravitational perturbations from other planets. Saturn, by contrast, sits in the relatively calm outer reaches of the solar system, where gravitational influences are weaker and more stable, allowing ring systems to persist for hundreds of millions of years. The geological evidence suggests that Earth might have had rings in the distant past, but lost them due to these destabilizing influences. The giant impact hypothesis, which explains the formation of our Moon, proposes that a Mars-sized object called Theia collided with early Earth about 4.5 billion years ago. This catastrophic collision would have ejected enormous amounts of debris into orbit around Earth, potentially creating a spectacular but temporary ring system. Computer models of this ancient collision show that the debris from the Theia impact would have initially formed a disk of material orbiting Earth, much like the rings we see around Saturn today. However, this proto-ring system would have been unstable due to Earth's proximity to the Sun and the complex gravitational dynamics of the newly formed Earth-Moon system. Over a period of perhaps millions of years, this debris disk would have gradually coalesced to form our current Moon, leaving Earth without rings, but with the large lunar companion that now prevents ring formation. The composition requirements for stable rings also work against Earth having a ring system. Saturn's rings are composed primarily of water ice, which is abundant in the outer solar system, where temperatures are extremely cold. At Earth's distance from the Sun, water ice is much less stable and would tend to sublimate, transitioning directly from solid to gas when exposed to solar radiation. Earth's rings would need to be composed primarily of rocky material, which is denser than ice and more susceptible to gravitational perturbations that would destabilize ring orbits. The asteroid belt, located between Mars and Jupiter, provides another clue about why Earth lacks rings. This region contains countless rocky objects that could theoretically form rings if they were somehow transported to Earth's vicinity and broken apart within the Roche limit. However, the asteroid belt is gravitationally isolated from Earth's influence by Jupiter's massive gravity well. Jupiter acts like a cosmic barrier, preventing most asteroid belt objects from being perturbed into Earth-crossing orbits that could lead to ring formation. Earth's relatively small Hill sphere, the region around our planet where Earth's gravity dominates over the Sun's influence, also limits ring formation possibilities. Earth's Hill sphere extends to about 1.5 million kilometers, much smaller than Saturn's Hill sphere, which extends over 65 million kilometers. This smaller gravitational domain means Earth has less space available for stable ring orbits and is more susceptible to solar perturbations that can disrupt ring systems. The absence of shepherd moons around Earth represents another crucial factor in our planet's ringless state. Saturn's rings are maintained and sculpted by dozens of small moons that orbit within and around the ring system. These shepherd moons use their gravitational influence to confine ring particles to specific orbital regions, preventing them from spreading out and dissipating. Earth has only one large moon in a distant orbit, providing no shepherding effects that could maintain ring stability. Current space debris around Earth provides an interesting modern example of why natural rings don't form around our planet. Humans have launched thousands of satellites and created millions of pieces of orbital debris that could theoretically be considered artificial ring material. However, this debris doesn't form stable ring-like structures because of the same gravitational perturbations that would affect natural rings. Most orbital debris either falls back to Earth within decades due to atmospheric drag and lunar perturbations, or gets boosted to higher orbits where it escapes Earth's gravitational influence. The lack of recent large impact events in Earth's vicinity has also contributed to our ringless state. Ring formation typically requires catastrophic events like asteroid collisions, comet disruptions, or moon-shattering impacts that can inject large amounts of material into ring-forming orbits. Earth's current neighborhood is relatively quiet compared to the early solar system, when such events were much more common. The lack of available raw material for ring formation means Earth would need to capture objects from elsewhere in the solar system, which is extremely unlikely given current orbital dynamics. Earth's magnetic field adds another complication to potential ring stability. Our planet's magnetosphere interacts with charged particles in ways that can alter their orbits over time. While this effect would be relatively minor compared to gravitational perturbations, it represents another mechanism that would gradually destabilize ring particles and contribute to ring system decay over long time periods. The evolution of Earth's orbit over geological time has also played a role in preventing ring formation. Early in solar system history, planetary orbits were less stable and more elliptical than they are today. Earth's orbit has gradually circularized and stabilized due to tidal interactions with the Sun and gravitational interactions with other planets. This orbital evolution has created the current configuration where Earth's distance from the Sun and orbital characteristics are particularly unfavorable for ring formation and maintenance. Atmospheric effects, while minor at ring altitudes, still contribute to Earth's inability to maintain rings. Even at altitudes of several thousand kilometers where rings would exist, traces of Earth's atmosphere create drag forces that gradually slow down ring particles and cause them to spiral inward toward the planet. This atmospheric drag effect is much stronger for Earth than for the gas giants, which have much more extended atmospheres that don't reach into ring-forming regions. The timing of when Earth might have acquired rings also matters significantly. If Earth had somehow acquired rings early in its history, when the Moon was closer and tidal forces were stronger, the rings would have been destroyed even more quickly than they would be today. If rings formed too late in Earth's history, after complex life had evolved, the environmental disruption from ring formation might have triggered mass extinction events that would have fundamentally altered the course of biological evolution. Comparative planetary science reveals that ring systems are actually quite rare and require very specific conditions to form and persist. Of the 8 planets in our solar system, only the 4 gas giants have substantial ring systems, and even among these planets, only Saturn has the spectacular, long-lived rings that capture popular imagination. The terrestrial planets Mercury, Venus, Earth, and Mars all lack significant ring systems, suggesting that the conditions required for terrestrial planet rings are extremely demanding. So why doesn't Earth have rings now? The answer lies in a combination of factors that make our planet uniquely unsuited for ring formation and maintenance. Our large moon creates gravitational perturbations that clear out potential ring material. Our proximity to the Sun creates additional destabilizing forces, and our location in the inner solar system exposes potential rings to environmental conditions that favor ring destruction over ring preservation. Earth's current ringless state is not an accident, but the inevitable result of 4.5 billion years of gravitational evolution in a planetary system that favors ring destruction over ring creation. While this means we miss out on the spectacular beauty of planetary rings, it also means we have the large, stable moon that creates ocean tides, stabilizes Earth's axial tilt, and may have been crucial for the evolution of complex life on our planet. After exploring every aspect of what Earth would be like with rings similar to Saturn's, we arrive at a remarkable scientific conclusion that challenges our assumptions about planetary possibilities and reveals the incredible complexity of the cosmic forces that shape our world. The concept of Earth having rings isn't just imaginative speculation or science fiction fantasy, but represents legitimate scientific inquiry, supported by rigorous mathematical modeling, computer simulations, and peer-reviewed research that has been conducted by some of the world's leading planetary scientists and astrophysicists. The scientific legitimacy of Earth rings rests on solid theoretical foundations that have been extensively tested and verified. The same physical laws that govern Saturn's magnificent ring system, Newton's laws of gravitation and motion, Kepler's laws of orbital mechanics, and the principles of tidal forces and gravitational resonances, all apply equally to Earth. Computer models using these established physical principles consistently show that Earth could indeed support a ring system within the Roche limit, the well-understood zone where tidal forces can overcome gravitational self-attraction to create ring-forming conditions. What makes this scientific exploration particularly compelling is that it isn't based on speculation about unknown physical processes, but on the application of well-established science to a hypothetical but physically plausible scenario. Every major conclusion we've reached about Earth's potential rings, from their orbital mechanics to their climate effects, to their impact on space exploration, emerges from the same type of rigorous scientific analysis that scientists use to study Saturn's actual rings or to plan real spacecraft missions. The orbital dynamics of Earth's hypothetical rings have been modeled using the same sophisticated computer programs that NASA and other space agencies use to track satellites and plan interplanetary missions. These simulations reveal that ring particles would indeed follow stable orbits within Earth's Roche limit, though they would face greater long-term instability than Saturn's rings due to perturbations from the Moon and Sun. The mathematics of these orbital calculations are precise and unambiguous, based on centuries of astronomical observation and theoretical development. Climate modeling studies have used actual global circulation models, the same types of computer programs used to study climate change and weather prediction, to explore how ring shadows would affect Earth's atmospheric systems. These studies, published in legitimate scientific journals, show that ring-induced changes in solar radiation patterns would indeed create measurable effects on regional climate systems, ocean circulation patterns, and atmospheric dynamics. The effects wouldn't be catastrophic on a global scale, but they would be real and significant enough to alter local weather patterns and ecosystems. The visual appearance of Earth's rings, as seen from the planet's surface, has been calculated using the same principles of geometric optics and astronomical observation that astronomers use to predict eclipses, planetary transits, and other celestial events. The dramatic differences in ring appearance between equatorial and polar latitudes aren't artistic speculation, but mathematical certainties based on the geometry of how ring planes intersect with viewing angles from different locations on Earth's surface. Space exploration challenges posed by Earth's rings have been analysed using actual spacecraft engineering principles and orbital debris tracking methodologies currently employed by space agencies around the world. The collision risks, navigation challenges, and mission complexity issues we've discussed are based on real-world space engineering experience and the same risk assessment techniques used to design current satellite missions and space station operations. The biological and evolutionary effects of rings have been explored using established principles of evolutionary biology, ecology, and environmental science. The predictions about how organisms would adapt to altered light patterns and climate conditions are based on our understanding of how species have actually responded to environmental changes throughout Earth's history. These aren't wild speculations, but scientifically informed projections based on documented evolutionary mechanisms and ecological relationships. Perhaps most importantly, the entire concept of Earth having rings gains scientific credibility from our growing understanding of planetary ring systems throughout the solar system. Every planet in our solar system beyond Mars has rings of some type, and astronomical observations have revealed ring systems around planets orbiting other stars. Ring formation and evolution represent normal planetary processes that occur under the right conditions, not exotic phenomena that require special explanation. The temporary nature of Earth's rings, one of our key conclusions, emerges directly from mathematical models of how ring particles would behave in Earth's specific gravitational environment. Unlike Saturn, which sits in the relatively stable outer solar system, Earth's proximity to the Sun and large Moon create destabilizing forces that have been precisely calculated using established celestial mechanics. The timescales for ring decay we've discussed, thousands to millions of years, come from detailed computer simulations that track the orbital evolution of millions of individual ring particles over extended time periods. The mechanisms by which Earth could acquire rings, primarily through tidal disruption of objects within the Roche limit, represent well-documented physical processes that we observe happening elsewhere in the solar system. Mars's moon Phobos is currently spiraling inward and will likely be torn apart by tidal forces within 50 million years, providing a real-world example of exactly the type of process that could create rings around Earth. The physics of tidal disruption is thoroughly understood and has been confirmed through observations of comets breaking apart near Jupiter and other massive planets. Cultural and societal impacts of Earth's rings, while necessarily more speculative than the physical science aspects, are grounded in legitimate anthropological and historical analysis of how celestial phenomena have influenced human civilization throughout history. The patterns we've identified, such as the integration of celestial events into religious practices, navigation systems, and architectural design, are based on documented historical examples of how humans have responded to prominent sky features like the Sun, Moon, and bright planets. The scientific methodology underlying our entire exploration of Earth's rings follows the same approach used in legitimate planetary science research, starting with established physical principles, applying them to specific conditions through mathematical modeling and computer simulation, and then interpreting the results within the context of broader scientific understanding. This isn't speculation or science fiction, but the application of scientific method to explore the consequences of a physically plausible scenario. Research institutions around the world, including NASA's Jet Propulsion Laboratory, the European Space Agency, and major universities, have conducted studies on planetary ring dynamics, orbital mechanics, and the climate effects of altered solar radiation patterns that directly support our conclusions about Earth's hypothetical rings. The scientific literature contains dozens of peer-reviewed papers exploring various aspects of planetary ring systems, tidal effects, and orbital evolution that provide the foundation for understanding how Earth's rings would behave. The computational tools used to model Earth's ring systems are the same sophisticated programs used for real-world space mission planning and planetary science research. Software packages like SPICE, developed by NASA for spacecraft navigation and planetary science, and advanced climate models used by international research organizations, provide the computational framework for exploring how Earth's rings would affect everything from spacecraft trajectories to global weather patterns. The interdisciplinary nature of Earth ring science, combining elements of astronomy, physics, geology, biology, and even anthropology, reflects the comprehensive approach needed to understand complex planetary systems. This interdisciplinary methodology is characteristic of modern planetary science, where understanding planetary environments requires integrating knowledge from multiple scientific disciplines. The educational value of exploring Earth's hypothetical rings extends beyond simple curiosity to provide insights into fundamental scientific principles that govern planetary systems throughout the universe. By understanding why Earth doesn't have rings and what would happen if it did, we gain deeper appreciation for the complex factors that shape planetary environments and the delicate balance of forces that make Earth suitable for life as we know it. The technological implications of Earth ring research have practical applications for current space exploration challenges. Understanding how to navigate spacecraft through debris fields, predict orbital evolution under complex gravitational influences, and assess collision risks in cluttered orbital environments are all relevant to current space exploration activities and future missions to asteroids, comets, and other small bodies throughout the solar system. So what is the scientifically verified final takeaway about Earth having rings like Saturn? The concept is scientifically legitimate, mathematically sound, and technically feasible, based on well-established physical principles and extensively tested theoretical frameworks. Earth could indeed have rings. They would be spectacular and transformative, and their effects on everything from climate to culture to space exploration would be profound and measurable. While the probability of Earth naturally acquiring rings in the near future is extremely low, the scientific exploration of this possibility provides valuable insights into planetary science, orbital mechanics, and the complex factors that shape planetary environments throughout the universe. The study of Earth's hypothetical rings represents science at its best, using rigorous methodology and established principles to explore possibilities that expand our understanding of planetary systems and our place within them. Whether or not Earth ever actually acquires rings, the scientific exploration of this possibility enriches our understanding of the cosmos and demonstrates the power of scientific thinking to illuminate the hidden complexities of the world around us. In the end, Earth's rings may remain forever hypothetical, but the scientific insights gained from exploring this possibility are entirely real and scientifically valuable.